Hello, in this short little video we will talk about redox titrations. And the reason this video is short is because you already know how to do titrations. We've done this with acids and bases all the time. The only difference here is that now it's a different chemical reaction, and your stoichiometry might not be one-to-one. Other than that, you know how to do this. So I'm just going to talk about it, show an example, and then we'll be done. Okay, we use redox titrations a lot in wet chemical analysis because they can allow us to determine concentrations of things beyond acids and bases, and that's useful. Concentrations, amounts, etc. And so, for example, we can take the reaction between permanganate and manganese ion and use that for our titration. This goes from really dark pink to almost colorless, and so that sharp color change is really useful for a titration. You don't have to add an indicator. And so this is one of the reasons why you need to know how to balance redox reactions, because if you have it balanced, then you can do a titration. If it's not balanced, then you'll get the wrong answer. Now, your requirements for a titration are, 1, that the reaction goes quickly, so that you can titrate it in real time, and 2, that the reaction is quantitative. So that means that the reactants go completely to products. Because if your equilibrium constant is somewhere, in the middle of the complete reaction, then you can't do a titration on it, because then you have to think about equilibria concerns, and that's a big problem. So this reaction is quantitative. That's useful. Just like the reaction between H plus and OH minus is quantitative. That's useful. So now here, your difference is that at the equivalence point, you have a 1:5 ratio between permanganate and iron. Other than that, it's just like we did before. So let's show an example. Say we have this reaction, and we have some volume of some concentration of permanganate, and we're titrating that against 25 milliliters of iron sulfate. And this is a soluble ionic compound. This will deliver iron 2+ into solution. This permanganate is a soluble compound. It'll deliver K+ and permanganate into solution. That's fine. So we can use this reaction as written, use it net ionically, because that makes our life a lot easier. And our plan here is we're going to use the known volume and concentration of permanganate to find moles of permanganate right here. And then we can do the stoichiometry to go from moles of permanganate to moles of iron, 1:5. Then once we know moles of iron, you can take moles over liters to find concentration. Or who knows, maybe moles is the thing you want to know. Just depends on your outcome here. We want to find concentration, so we do this. We'll need the volumes in liters, because that makes it easier when you're using molarity. And then we're off to the races. We have our volume of potassium permanganate solution. And if you take molarity times liters, moles over liters times liters, you get moles. So we do this, and now we have moles of permanganate, or potassium permanganate, same thing. And then we use the mole ratio, and so we have 5 moles of iron for every 1 mole of permanganate. And now from here we have moles of iron. If you take moles over liters, you're going to get concentration. And then before we get the answer, let's double check that we canceled everything. Our liters cancel, our moles of permanganate cancel, so now we have moles of iron, moles over liters per iron, which gives us molarity, which is exactly what we want. So here's our molarity of the iron solution, and that's it, right? So you know how to do this already. This is just stoichiometry and titrations from the first semester of Gen Chem. It's just with a new reaction. So a couple practice problems on this. Practice till you are for sure going to get the answer right, and then you're good to go. Thanks for watching.